Ali, over to you.
Thank you so much. And yes, that's we in the royal sense, really, for how we test them. First of all, a big thank you for having me here to speak to you this evening. It's a real pleasure to be able to come and speak to what I'm sure is a very engaged and lively audience, and hopefully I can bring something interesting and something a bit new, as I'm sure you'll all be vaguely familiar with some of these topics following the past few years. So just very broadly, what I hope to speak a little bit about this evening is, first of all, a broad look at vaccination and the science of vaccination and how they work. How do these miraculous drugs achieve what they do, and what are we aiming for when we develop a new vaccine? And then looking at the process of where do they come from? How do we get a vaccine from nothing into millions of people's arms and saving lives around the world, and using the experience of the COVID pandemic and the vaccines that were developed for that as an example, hopefully an interesting one, because as was so eloquently stated, it's something that's impacted all of us over the past few years. And I'll be talking a bit from personal experience from the pleasure that I had to be involved with that. So just something to begin with. Does anyone know what the difference is between these two terms that are often used interchangeably, between vaccination and immunization, even often used as if they're the same word by doctors? Essentially, the difference is that vaccination is just giving someone a vaccine, whereas immunization actually means providing someone with a robust and effective immune response from a vaccine. So obviously, there are vaccines that don't work. And if you give someone a vaccine that doesn't work, you haven't immunized them, but you have vaccinated them. So there is an important difference there. So you will hear those two terms used interchangeably, but now you can seem really smug when you know what the difference is, and other people don't. So I thought it'd be interesting. This really is just me satisfying my own desire to talk about this topic, but to just talk a little bit about the history of vaccination, because it's fascinating. It's really interesting. So the first form of something that resembled vaccination was actually a practice that was called variolation. And this was practiced back in ancient Chinese culture. And it was actually for smallpox. I don't know, some of you may remember far back enough when smallpox was still around, perhaps, and when we were fortunate enough to eradicate it off the face of the earth. But it was a horrifying illness, a really desperately horrifying illness. It was essentially ubiquitous, so every single person would catch it at some point in their lives. And certain forms of it had up to a 50% mortality rate for the hemorrhagic forms. And it was so lethal that people were willing to accept very dangerous methods of protecting themselves from it. And variolation is not a very glamorous thing to do, but essentially what would happen is people would look for friends or relatives who had had smallpox and had a very mild case of smallpox, and they would pick off their scabs, and they would let the scabs dry, and they would grind the scabs into a fine powder, and they would snort the powder to inoculate themselves with a very mild form of smallpox, hoping that they would get a mild version of the disease and not one of the nastier versions. Variolation had a mortality rate of 1 to 2%, and yet it was endorsed by the Royal College of Physicians in London in the late 1700s because this was preferable to catching smallpox. So this was the sort of the preceding science to vaccination, and it was a disease that was so lethal that people would take a preventative medicine, as it were, that carried a mortality risk of 2% to try and protect themselves from it. Quite extraordinary. Wouldn't recommend it today. And we did move on a little bit. It took a little while, but this picture here is the cowhide of Blossom the cow. And this is the cow that belonged to Edward Jenner. Well, actually, it wasn't his cow. But this is the cow that Edward Jenner used to sample a scab of cowpox. Now, the story of Edward Jenner is that he actually wasn't the first person to recognise this. It was a chap called Bestie from Dorset who noticed it but didn't publicise it. But regardless, it's just because it's come from us down south. But Edward Jenner noted that milkmaids very frequently got cowpox and didn't seem to really ever get severe cases of smallpox themselves, if at all, and wondered if the fact that they were all catching cowpox as an occupational hazard was protecting them. And so he decided to test this out. And so what he did was he found poor Blossom, who had a case of the cowpox, and he took some of the lesion, and he found an 11-year-old boy and cut his arm and rubbed some of the cowpox lesion into the boy's arm, and then exposed him to smallpox. And the boy was absolutely fine. And he thought, wow, that's miraculous. And he tested it on many other people, including his own son, believe it or not. It took off from there, really. That was the evidence that he needed. And again, he provided this to the Royal College of Physicians in London as evidence. And this was sort of taken forward as a superior approach to variolation, because cowpox is much more mild than giving someone what you hope to be a very mild version of smallpox. And this is actually where the name vaccination came from, is vacca, is the Latin for cow. But this also was not without its own problems, because what was happening was that the material that people were passing from one to another to inoculate them with cowpox was often contaminated with other blood-borne diseases and things like that, and would make people very ill, and often very young children. And so this came with its own problems, because children would often die from the practice of vaccination, even though it was safer than what came before it. And then the next important part of our journey is Louis Pasteur, because up until this point, people really had no idea what they were actually doing. Right? They had made observations about these associations between, if you get mild smallpox, then hopefully you don't get a severe one, and if you get cowpox, then hopefully you don't get smallpox. Who knows why? Germ theory hadn't been around yet. They hadn't been invented. People still thought that diseases were spread by bad air, miasma, and this kind of thing. We go forward to this chap who's Louis Pasteur, who was one of sort of several people who brought germ theory to the fore. And Louis Pasteur is probably really responsible for generating the science of vaccination as we know it today. But it came about by chance, actually. So Louis Pasteur had a trainee, an associate, who was supposed to be killing some chickens with cholera, as one does. And the associate had forgotten to do it before he went away on holiday, and he had this delightful cholera broth that he left on the side and went away, came back, and thought, I was supposed to kill those chickens with the cholera. I'd better get on and do that before anyone realizes. And so he gave the chickens this old cholera broth, and they were fine. And he was like, oh no, my broth's gone bad. I'll get some new broth. So he got some new cholera broth and gave it to the chickens, but they were fine again. And the penny dropped at this point with Louis Pasteur. The famous saying is, fortune favors the prepared mind. And so he then had this theory, well, is exposing a chicken or people to a weakened or killed version of a germ a way of protecting them against it? And from there, really, we have modern vaccination science as it developed, and vaccines against anthrax and diphtheria and so forth were taken forward from this point. And then we move forward to people like Maurice Hillman, who worked for Merck, who developed about 10 or 15 different vaccines. And now we have vaccination science as it was today, through this realization that by exposing people to weakened or dead versions of a pathogen, that you could somehow protect them against virulent infection in the future. So how does that work? So I'm going to be completely honest with you guys. We don't understand the immune system, really. We have some very useful models of how we generally understand it to work, but it does lots of things that we wouldn't expect from the kind of models and the way we understand it, but it's very useful for understanding vaccines to explain it in this kind of way. But when you go and dig deeper, you'll find that there's all sorts of weird stuff happening that none of us get. But I'll try and explain it in the nice models that we like to put them in the compartments. So your immune system is really a description of any part of your body that is helping to protect you from invading pathogens. So other, life forms that want to come and make their home in you or eat you or otherwise hurt you. And we broadly split that into two groups. So on the left here, we have what we call your innate immune system. And this is really a non-selective immune system. This is the part of your immune system that will kill anything. So when it sees something that it doesn't like, it will kill it. It will go and kill it. And this includes sort of barrier bits of your immune system. So we consider your skin a very important part of your immune system. And if you break your skin, you'll notice that you're at risk of getting an infection because you've broken one of your barriers. And then there's obviously the cellular components and cells that recognize infection and go and gobble them up. And that's great. And the innate immune system is terrific. But what we're really interested in is the right side of the screen here, which is what we call your adaptive immune system. And this is not general at all. Your adaptive immune system is in fact highly, highly specific. And where your innate immune system is capable of recognizing anything and responding immediately, your adaptive immune system is not the same. It needs to have seen something and decided that this is a threat that you need to learn how to neutralize. And then over preceding days and weeks, it can prepare itself to do so. And then the next time you see it, it is ready to go within a matter of hours. And so vaccination works on your adaptive immune system predominantly, bearing in mind that this is all a gross overgeneralization of a system we don't fully understand. So this is a sort of scary looking diagram, but I'll try and go through it very slowly to just give you a brief overview of what actually happens when we give you a vaccine. So we've got our nice needle at the top there, which contains a vaccine. And we've got our vaccine antigen. Now, I'll talk a little bit more about the different technologies that we use for vaccination, but broadly speaking, a vaccine will always contain some part or the whole of the pathogen you want to protect yourself against. And you're training your body to recognize the pathogen, either by presenting it with a part or sometimes the whole thing. So we inject that into your muscles. Then we've got this wonderful thing called a dendritic cell that goes around looking for things that shouldn't be there. And it picks up these antigens and it takes them. It swims off down into a regional lymph node, and there it presents them to T cells, which are part of your adaptive immune system. Now, T cells and B cells are quite incredible, right? What your body does is it produces billions and billions of these cells that each have a very specific receptor on them. And your body has made each of these different cells with a different receptor that could identify almost any different type of protein that could possibly be presented to them, right? So they're all different. And what happens is your dendritic cell comes and it's found this bit of a pathogen and it presents it, and a T cell that has the right receptor that will recognize it will come along and go, aha, my time has come. And this is its signal. Go forth and multiply. Go and tell your friends that have the similar receptors. We need more of you. And that's where the cascade kind of begins. Is these cells then go off and they start multiplying. And we have different types of T cells. So there are T cells that are called CD8 T cells, and these are killer T cells. And these are the ones that are actually going to go out and do the killing of the bacteria or the viruses that the cells that contain nasty viruses. And you have your CD4 cells, and these are helper cells. And these are cells that go off and they tell antibody-producing cells, make some antibodies against this, or they help stimulate other killer T cells. And then what happens is you get this rapid proliferation of these cells, and this all happens acutely, and then you develop these longer-lasting cells that hang around, ready to go the next time that this protein or this pathogen is encountered, right? So obviously the first time this happens, you've just got a very small number of these circulating cells. They rapidly, exponentially grow and replicate, and then you have this bank of memory cells ready to go next time you encounter them. And they go and live in your bone marrow, and they're ready to go forever. And of course, a very important part of this, and you'll have all been hearing loads and loads about antibodies during the pandemic, is your B cells, and these are antibody-producing cells. And they are ready to make antibodies specifically against that protein that's been presented to them, that's been shown this shouldn't be here. You need to be ready to fight this. And antibodies are great. They do all sorts of things. So for viruses like the COVID virus, SARS-CoV-2, what they'll do is they'll bind to that bit of the protein they need to so that the virus cannot get into your cells. They'll also latch onto bacteria as a signal, going, hey, over here, killer cells, come kill this one. And sometimes they'll do direct damage themselves and actually directly harm the pathogen. They do all sorts of things. Very clever molecules. I like them. Okay, so let's talk about some of the different technologies and how they all work. So I guess the most obvious one is killed whole cell of virus. And this is the kind of thing that Louis Pasteur had done, which is you take a pathogen that if I was to serve it to you neat, would not be good for you at all. And so instead what we do is we smash it up a bit. Perhaps we give it a bit of ionizing radiation and make it unable to do anything, or we kill it in other ways. And then we just present that dead version to you. Now, the dead version can't hurt you, but it's got all the bits that your body needs to recognize it. So often that will be enough by itself. We've got subunit or conjugated vaccines. So a lot of the childhood vaccines are produced in this way, and this contains just one portion of the outside, a recognizable bit of a bacteria perhaps, sometimes attached to something else that makes it more easily recognizable. And again, this is injected into your body so that your body can learn to recognize this one specific portion it needs to protect you. And then you have toxoid vaccines. So these are not vaccines actually against the pathogen itself, but against the toxin that those pathogens would produce that would harm you. So for example, against the tetanus toxin or diphtheria toxins. We have virus-like particles, so this is complicated, but these are essentially molecules that look like viruses, but aren't actually the whole virus made synthetically. So the human papillomavirus vaccine is one of this kind. And then we have live vaccines, which are usually attenuated. So this is a live version of the virus that you may otherwise encounter, or the bacteria or whatever, but it's been weakened in a way so that it cannot harm you through vaccination, but is alive enough to stimulate a robust immune response, so your body knows to take it seriously and then is more prepared for next time you get there. One of my favorite versions of this actually is the influenza vaccine. I don't know how many of you are aware of the nasal flu vaccine that's used mainly for children, but this is a brilliant vaccine. It's cold attenuated, and what this means is that it can only survive at low temperatures. So when you squirt it up a child's nose, it's quite happy there, it's cool, and it can replicate, and it has a great time, and it will stimulate lots of good immunity in there. If it tries to go any lower, like into the lungs or anywhere it could actually cause serious illness, it can't replicate, it dies. So it's attenuated, it can only survive in your nose. Genius. Love it. So that's a bit about vaccines and how they work. I'm trying to think if there's anything I've not said before we move on to thinking about how we test them. Oh, you've got a question, sir. Go on. Yes. No, I'm going to come on to that. We're going to talk all about COVID just after this bit. So, what are the things we need to think about? Well, I want to make a vaccine. Oh, it's got to be safe, okay? I mean, and when I say safe, I mean it's really got to be beyond safe, because this isn't like a normal medicine that I'm going to give someone who's got a problem that I want to make better, that they can probably tolerate a few side effects or something else because, it will make them feel better overall, and that's why I'm giving it. We're giving these generally to well people to stop them from having a problem. So what we really don't want to do is give them a problem if they may never have had a problem in the first place, particularly because thanks to herd immunity, which is a term we'll all have heard an awful lot about over the past few years, if enough people are immune to a pathogen, it cannot spread, and so the risk of transmission drops precipitously. And now actually one of the main reasons we vaccinate so many children against things like polio or Haemophilus influenza B and things like this are not because they're circulating, they're not, they've vanished, but we want to keep them vanished, okay? So the likelihood is kids are not going to ever encounter those things, hopefully. So if I'm going to vaccinate the kids against them, the vaccine needs to be really safe, because I'm protecting them against something probably they're never going to encounter unless we don't vaccinate everyone, which is why we still have to vaccinate everyone. So super safe. Reactogenicity is important too, because safety is really talking about not feeling bad, but bad things happening to you, right? So sort of serious illnesses, whereas reactogenicity is just feeling bad. And some vaccines do make you feel bad. My recent flu vaccine did not make me feel fantastic for the first 24 hours after I had it, which was a bit of a shame because normally I'm quite robust to the flu vaccines, but not this year. But we do have to consider this, especially for low-risk pathogens. An example of this was, and is, the COVID vaccine for children, where the risk to children from COVID illness is really very low, sort of on par with very minor seasonal respiratory viruses. And the COVID vaccines were very reactogenic, and this was actually quite a serious concern in dosing these vaccines, was if it made children feel really rubbish, it just would not be worth vaccinating them. So we take this very seriously as well. And then, of course, it's got to work, right? It's no good vaccinating people if we're not immunizing them. So when we're doing our clinical trials of vaccines, we are really looking at these three major components. It has to be safe first and foremost. Ideally, it needs to have an acceptable reactogenicity profile, and it has to work. So it has to do the thing we want the vaccine to do. And sometimes we want vaccines to achieve slightly different things, which we can talk about more in a moment. So COVID. This is the virus that causes COVID. This is the SARS-CoV-2 virus, okay? Don't worry about most of what's on this screen, but what I want you to look at the top there is the spike protein, which is so called because it's spiky. So the reason that these viruses are called coronaviruses is they have these spikes sticking out at the top, and it makes them look like a crown, and corona is Latin for crown. And the way that these viruses enter your cells and do damage is that this protein binds to a protein on the outside of your cells called ACE2 or TMPRSS, and it is then able to open your cell membranes and get inside and replicate and then make lots more viruses and then kills your cells, and all the viruses come out and they bind to more cells and they go in and they replicate, and so on and so forth. And so probably in terms of pathogenicity for human beings, this protein is the protein that we're most interested in. It obviously needs lots of other bits and pieces to do its job, but this is the key. And we know that this is the key because this is the key for other coronaviruses like SARS and MERS, and that was a very beneficial thing for us. Just going back to that, but this was actually really key because one of the reasons why we were able to so rapidly produce vaccines for this is that people had been working on vaccines for MERS and SARS for quite some time and had identified that the spike protein was the key thing. So everyone was spike, spike, spike. We know we've got to do spike. This means that when we found that this new virus was a coronavirus, everyone was like, right, what is the genetics of the spike? That's what we're targeting. We'll make vaccines for that. We didn't have to do this whole thing of faffing about and going, oh, what are the different proteins? What do we need to target? What's the function of this? What's the function of that? We knew. Giant head start. That was a game changer. So, how do the vaccines work? So, the ones that we're most familiar with are for COVID-19 are the mRNA vaccines. So you will probably know them mainly as the Pfizer or the Moderna, mainly Pfizer in this country. But this was a brand new technology in terms of authorization. So there were no existing vaccines that had actually been deployed at scale using this technology before. And it's a great technology, and it's not one that we've mentioned. And the way that this works is you take an antigen, a portion of the virus, and for us here, it's the spike protein, but you don't put the spike protein in the vaccine. What is in your vaccine is code for your cells to tell it how to make the spike protein. And this code is in the form of messenger RNA. So your body uses messenger RNA to make its own proteins. And actually, this is how all your proteins are made, is that messenger RNA reads your DNA. And then that's part of the process of translating it into proteins and making all of your machinery. What we have here is a bit of a cheat, a bit of a hoodwink. So we're delivering a external mRNA into your cells, and here you can see this lovely orange ring around it is what we call a lipid nanoparticle, and this is a coating that keeps the mRNA stable and allows it to get into your cells so that they'll make it. So without that, the mRNA would vanish in milliseconds. So you can see that in the middle here, the lipid nanoparticle allows the mRNA into your cell. It makes it into spike proteins, and then the spike proteins come out, and your dendritic cells say, "Ooh, what's this? This shouldn't be here. And it picks it up and it takes it and shows it to your lymphocytes, which are your T cells and your B cells. And then you make an amazing immune response ready to fight the actual virus when it comes in. And you've got antibodies that can bind to that spike protein, which means that it can't bind to your receptors and get into your cells. And that you have T cells that are ready to come and gobble up all of the virus-infected cells. Very clever. So that's just one type. We'll talk about some of the others. So broadly speaking, we can categorize mRNA vaccines under nucleic acid vaccines. So this doesn't just include mRNA, but could include DNA, because also DNA can code for vaccines itself. It just needs another layer of translation, because then it needs mRNA to come and read the DNA and make proteins, but works in a very similar way. And actually, this is how the virus vector vaccines works. So any Oxford AstraZeneca vaccine recipients in the house tonight? Yes, plenty of you. Fabulous. What a great vaccine it is. So the way this works is, again, different to everything else that we've said, and again, was a new technology to be deployed at scale, although it had been used a bit more in the US Army and some others. But what we do here is we take a different virus, and in the case of the Oxford vaccine, it was a chimpanzee adenovirus. Yeah, sounds a bit weird, right? But don't worry. What you do to that is you make it replication deficient. So you genetically modify the chimpanzee adenovirus so it can't replicate. So it thinks it's really clever and it gets into your cells, and then it's like, oh, shucks, that's it. I'm out of game. I've got nothing else. But what else you put inside it is DNA that codes for the spike protein. So the viral vector is able to get into your cells. It releases this DNA. The virus then has got nothing else to do, but your body will see the DNA and it will produce the spike protein on that basis. So again, it's another vaccine that doesn't actually contain any specific bits of the virus or bacteria, but contains the code that allows your body to make it and then produce an immune response against it. Other vaccines that work in a similar way are the Janssen vaccine, which we didn't have much of in this country, but this was using human adenovirus, adenovirus 26, and Sputnik, which was actually 2 different replication-deficient human adenoviruses. And that was the one that was used in Russia. More like traditional vaccine technology was what we would call purified protein. So this is very straightforward, a vaccine that basically just contains the spike protein. So they used moths, actually, moth cells to genetically engineered to produce the spike protein in the Novavax vaccine. And that was combined with an adjuvant. Oh, that was the thing that I haven't talked about. I haven't talked about adjuvants. Well, now is a great time because we're talking about the Novavax vaccine. So in some vaccines, when we introduce a bit of a cell or a virus, or even sometimes if we introduce the whole thing but in a killed fashion, we put it into the body and the body looks at it and goes, meh, doesn't seem that important, and doesn't produce an immune response. That is not very predictable. Okay, so we don't always know when that's going to happen, but obviously we find out quite early that that happens. So there's no problem with the antigen. It's a part of the pathogen, but we need to tell the body, hey, there's something here you need to recognize and you need to produce an immune response against. And the way we can do that is with things called adjuvants. So it's something that you add into the vaccine to stimulate what we would call a danger signal, right? Something to tell the body, no, pay attention to this. And they actually do that by triggering the innate immune system. So these very generic receptors that would pick up kind of any pathogen at all. The innate immune system being stimulated tells the adaptive immune system that it needs to wake up and get involved. And we don't actually understand very well how a lot of adjuvants work. It's still black magic, like most of immunology, sadly. But the Novavax vaccine contains an adjuvant for this reason, and it's quite a new one to practice. So it's been in clinical trials for a long time in lots of vaccines, but it's an adjuvant called Matrix M. And then finally, again, very traditional, we've got killed virus. So this is just literally you take the SARS-CoV-2 virus, you kill it, you inject it. Well, at least that's what the Sinovac vaccine is like. The Valneva vaccine, which was the one that was trialled in the UK, and we even purchased a manufacturing facility for it and then never made it or used it. But the Valneva vaccine does contain an adjuvant as well called CpG, again, to stimulate the immune response. And isn't it interesting that this virus is a really immunogenic virus, and the spike protein is a really immunogenic protein, but if you just put dead virus into the body, it kind of shrugs its shoulders, and you need an adjuvant to stimulate it. Very strange, very unpredictable. Okay. So that's about how vaccines work. How do we get them into people's arms? So we do this through usually a very long process, mainly a long process because it just takes a lot of time to go through the various levels of bureaucracy and finish the trials. But obviously for COVID, we were able to do it very quickly. But there's 5 stages, being generous, because the stage that's before all of this is the preclinical stage. So this is the basic science of identifying the antigens that are most likely to be immunogenic. And this is done in a variety of ways, largely by finding sort of mammals that have similar immune responses to various pathogens and basically testing them by giving them antigens and seeing, do they respond well, and are these good candidates? There's more fancy ways of doing it that I will talk about in a while. But you have to go through this whole shtick of preclinical testing in animals and things, and giving animals like 40 times the dose that you would ever plan on giving a human being to see what would happen if you just massively overdosed them, what would be the side effects, and all of this kind of stuff. So we've got actually a pretty good idea of what we're getting by the time we even get to humans, because you've got to do a lot of stuff before you get to that stage. So when we run clinical trials, we get this whole thing called an investigator's brochure, which is just reams and reams and reams of preclinical data of all the stuff that's happened in the animals when they've given it to them, to the different types of animals at these absolutely insane doses. It's a really weird document, but very interesting if you're interested in that kind of thing. And then we get to the fun stuff, in my opinion. We get to the clinical trials, and we have really 4 stages of clinical trials. And again, we put these all into boxes, but there gets blurred lines in some instances. But it's nice to think of it in this way. Phase 1 is just about safety, mainly. What you're really doing is you take a very small number of people and you give them the vaccine and you watch them very, very, very closely. Every day you ask them to fill out a diary saying exactly what's happened to them. You take regular blood tests looking for any signs of any untoward incidents or effects. And you're really looking for major safety signals, right? You're looking for something bad to happen, hoping it doesn't, expecting it shouldn't, because as I said, we know quite a lot by this stage. And then for non-vaccines, it's also a lot about looking at what is the best dose. So you'll start at very low doses. And in fact, actually, I say that's not for vaccines. We do this for vaccines as well. You start at very low doses, check they're fine. Increase the dose a bit, check it's fine. Increase the dose a bit more. And really, you're looking for the sweet spot, okay? So you'll increase it, checking that all of the doses are well tolerated. And if you find that actually you've got up to your sort of upper half of the dose range and people are feeling, more rubbish as you increase the dose, but you're not getting any more immune response, then you can drop it back down and actually you'll get a more tolerable profile and probably the same amount of immunity. So you're dose finding, looking for safety. And then we move on to efficacy. So now we'll take a few more people, maybe a couple of hundred people, and actually now we're mainly interested in the immune response, still looking for safety signals because vaccines have got to be really safe, really, really, really safe. So we'll take a few hundred people, maybe at one dose, the best dose that we found. Sometimes if we're not sure from the phase 1, because it was really small, we might do a couple of doses at phase 2, but we're just looking for a couple of hundred people and we're looking for efficacy. Now, efficacy is a really specific term in clinical trials because what it means is the drug has done what you expect it to do in the body, right? So in this case, it will be, for vaccines, we're looking for biological evidence of an immune response. So have you made antibodies? Are your T cells active against that specific protein? So we're looking at all these things in the blood, right? Because that's important. But then moving on to phase 3 is when we're looking at effectiveness. And the difference between efficacy and effectiveness is efficacy is the drug doing in your body what we'd like it to do, and effectiveness is the drug causing the outcome that we want it to cause. So if in phase 2 I saw great immune responses in all the participants in my clinical trial, and then I recruit tens of thousands of people in my phase 3 trial, and there was no difference in the rates or severity of infection in the 2 arms of the trial who got the drug and didn't get the drug, my drugs failed, right? It didn't matter that it caused an immune response I wanted. It hasn't resulted in the outcome that I wanted to achieve. And that can be different things for vaccines, right? So some vaccines are really good at reducing the severity of illness, okay? So if you get the infection, you're just much less likely to need to go to hospital or ICU or even maybe feel really rubbish, okay? Some vaccines will just prevent infection completely. This is what we long for. Many vaccines don't do that so well. It's very difficult to produce robust immune responses against some things. But some vaccines will produce lifelong, robust, neutralizing immunity against infection, right? So for measles, for example, after a vaccine, we estimate for your antibody levels to drop by about half would take about 200 years, right? This is how strong and how robust that immunity is, right? And it prevents infection altogether. So we're sometimes looking for different things. And sometimes what we're looking for changes as time goes by, which again, we'll discuss in a moment. But yes, so effectiveness, that would normally be in a randomized control trial that would either be placebo controlled if there was no existing vaccine that works, okay, so we just test it against not having anything. Sometimes it will be against an existing vaccine, right? Because if something already works, we're not going to enroll you in the trial and not give you the thing that we already know works because it's not ethical, right? We can't withhold an effective treatment from you. So then we test it against the best existing standard of care. And this is one thing that I'll just mention. You'll hear, I don't know if any of you come across kind of the anti-vax sentiment, but one of the big things that gets talked about a lot is that, the vaccines haven't been tested against placebos, right? The existing vaccines that we give to children haven't been tested against placebos. That's because there were already effective existing vaccines that we couldn't withhold from children to trial the new ones. So we tested the new ones against the ones we already knew worked and were safe, because we can't not give children effective vaccines that we already have, okay? So it's true that a lot of the existing vaccines in the childhood schedule weren't tested against placebo. That's because I'm not going to withhold a measles vaccine from a child when I've got one that already works really well. So just in case you come across that myth. And then the final one is phase 4. This is what we call post-marketing surveillance. So normally what would happen is after a phase 3 trial, the drug company goes, haha, look, my vaccine works. I stopped all these people from getting sick. That's great. Give it to everyone. And so the regulators go, yeah, seems fair. You can give it to everyone if you want. And then the Joint Committee on Vaccination and Immunisation do their calculations and go, yeah, seems cost effective. This is worth giving to everyone. And then the government gives it to everyone. And then we've got to look really closely. Because with the best will in the world, major safety signals that come up from vaccines don't appear in clinical trials because they're too rare. Even when you have tens of thousands of people in a clinical trial, you have events that maybe only occur in 1 in every 100,000 vaccines. But if you then give them to 70 million people, okay, that's then going to happen to quite a few people. And so this is our post-marketing surveillance. And sometimes this is done in clinical trials in very large numbers. And sometimes actually post-marketing surveillance is just done in what we call observational studies. So we just have to look at people who received the vaccine compared to those who didn't, or historical controls. But it's a very important part. So some examples of some of the stuff that I've been involved with during COVID. So I'm going to talk about the 2 major clinical trials, the 2 clinical trials that I was most involved with, going through the different stages. So the first one's a really interesting study. So this is a phase 1 vaccine trial of a candidate vaccine against all Sarbeco coronaviruses. So coronaviruses are a big family, right? There's lots of them, but the ones that have tended to cause most problems for humans are what we call Sarbeco viruses. And this is SARS and SARS-CoV-2. And these are the ones that are recognized to sort of be most close to tipping over the edge from animals into humans. And so what we'd like is a vaccine that would prevent infection or severe illness against all of those viruses, or even better, provide really robust protection against all variants of the SARS-CoV-2 virus. Because as you will have all heard many times in the news recently, the virus keeps mutating, because that's what viruses do. And every time it does that, it's able to slightly evade the immunity that we've already produced, because that spike protein has changed its appearance, right? So we neutralize it less readily. So it'd be great to have a vaccine that would cover us against all of them equally effectively. So that's what this vaccine is. And this is great. I'm just going to tell you this because it's so interesting. The way that this vaccine was devised was using, it's a proprietary technology from our partners in Cambridge, and it's called DOS Synvax, and that stands for Digitally Optimized Synthetic Vaccine, right? What they do is, rather than just taking a virus or a bacteria and finding a protein on it and thinking, right, let's target that one, what they've done is they've looked across the whole family of Sebecoviruses and looked at all of their spike proteins and looked for the bits of those that are conserved, so the bits that are shared between all of them, and then looked at the different sections of it that when you give them to animals seem to stimulate a really robust immune response. And what they've done is they've made an entirely new antigen, right? A completely novel spike protein resembling antigen that's been synthesized to hopefully cause that broad protection across all the Sebecoviruses. Fascinating. I love it. And then this was what we call a dose escalation first in human study. Okay. So what we did was we took a very low dose of the vaccine, which is actually, the other great thing about this vaccine is it's delivered into the skin, not the muscle, and that means it doesn't need a needle. So this vaccine is delivered using a puff of air, using air pressure. And so it feels kind of a bit like being hit with an elastic band, yeah? But no needles, because people don't like needles, so that's another good thing. And then we escalate the doses in a stepwise fashion. So what we did was we would give 9 people 0.2 milligrams in dose 1, and we would wait till they had all gone 3 days post-vaccination, and we'd check on them every day and make sure they're feeling all right and there's no signals of anything going too bad. They all seem all right. Good. We have a safety review meeting. We present the data to some external people not involved in the trial, and we say, here's all our safety data. Can we increase the dose? And they say, go ahead. And then we go up to 0.4 milligrams, and we do the same thing again. We vaccinate everyone. We wait a few days. We collect all the data. We prepare a report. We take it to these people outside the trial and say, can we increase? And we keep going up and up and up. And we just a couple of months ago finally finished group 4 and vaccinated our last participant there. And so what we'll be looking at now is their immune responses in those different groups. So they get 2 doses of the vaccine, and then we'll be doing blood tests 4 weeks after their second dose. In fact, all of those blood tests are done now. And then we'll be looking for how well they've responded against not just COVID, but against SARS as well, the original SARS, looking if it's created that broad immune response. And if that is found to be safe and effective, then it will go into later phase clinical trials. And then this study was my baby. I'm very proud of this study. So this was the COV-Boost clinical trial. So this was the world's largest randomized controlled trial of COVID booster vaccines. And we would call this a phase 2 study. You could kind of call it a phase 4 study in some ways, but we'll call it a phase 2 for this purpose. Because what this was doing was taking a load of vaccines, some of which had already been authorized and some of which were still investigational products. And we were testing them as booster vaccines. Okay, so this was when the government was thinking, we've given loads of people 2 doses. Are they going to need any more? We don't know. Actually, as it ended up, we definitely did need them, so we were very pleased we started this trial when we did. But this is looking at the safety and efficacy of booster vaccines for COVID. And so efficacy means we're looking in the blood for evidence that the vaccine has done what we want it to do, which is increasing antibody levels and responses of those T cells, those killer cells against COVID-19. And we had 18 sites in this study. And we had lots of different subgroups based on people's ages, whether they were over or under 70 years of age, and based on what vaccines they'd received initially, whether it was 2 doses of Pfizer or 2 doses of the AstraZeneca vaccine, and seeing what happened to their immune responses when we gave them seven different COVID-19 vaccines and 3 of those vaccines at a half dose. And we did this in there were so many vaccines, we split all of our sites into 3 groups. And in each group, we also had a control arm. And they got a meningococcal vaccine, so a vaccine against the bug that causes meningococcal meningitis. And no one knew what they got, so it was a double-blinded trial. So you got a jab, you didn't know whether you got a booster vaccine, whether you got the control vaccine, which vaccine you got, and then we collected loads of data on the safety and efficacy of that study. And this was the trial that informed global policy on booster vaccines for COVID-19. It was great. It was a really fun time to be alive. And so what did we look at? We looked at reactogenicity, and this was fascinating because we found that reactogenicity was really dependent on what vaccine you got and what vaccine you had initially. So if you had 2 doses of the Oxford vaccine initially and we gave you a third, you were fine. If you had 2 doses of the Oxford vaccine and we gave you the Moderna vaccine, whoo, you felt it. You certainly felt it. And it was tolerable. You know, these people were okay, but, you know, there was a big difference. So you can see down in the bottom left-hand corner in these radiographs, they're beautiful, aren't they? Our statisticians made these. They're incredible. You can see this the big blue spike on fatigue, and this was on the people who got the Oxford AstraZeneca vaccine and then got 100 micrograms of the Moderna vaccine afterwards. And they felt really rough for about 24 hours afterwards. And that was really helpful to know. And then we looked at the immune responses. And there's a lot of stuff I could say about this graph. I won't bore you with it all, but I'll tell you what my favourite part of this was. So in these boxes, the red ones were people's antibody levels at the start of the trial before they got a booster vaccine. And then the green and blue boxes are their antibody levels 7 days after the vaccine and 28 days after the vaccine. And the bits where I've put the red arrow are on the left is people who got a dose of the Pfizer vaccine that had originally had the Oxford vaccine. You can see the massive jump in their antibody levels right away. And by the way, this is on a logarithmic scale. This isn't linear, so this is a huge difference. I love to see nodding when I talk about logarithms. It's terrific. What a great crowd. So on the left is people who got Oxford AstraZeneca and then got Pfizer. On the right is people who got a half dose of the Pfizer vaccine. And you can see it's almost identical. And this is really important, right? Because this was at a time when vaccines were very scarce. People were climbing over each other to try and get a dose of vaccine, right? There was a global shortage. It was a scandal, really, actually, because there were countries that couldn't get vaccine. And we suddenly found you could give someone half the dose of this vaccine as a booster, and it would provide basically equivalent levels of antibodies, which were the main surrogate of protection, so the main marker that predicted how likely you were to get infected subsequently. Fascinating. I could go on about that study all evening, but I won't. Oh, and we did so many sub-studies. This was because we were asked to, not just because we fancied it. So we gave a late booster. So we had to give people booster vaccines really early after their second dose in order to inform policy. So we were enrolling people who were only 3 months after they'd had their second dose, and we were bringing them in to give them a booster jab, because in order to get all of that done and get the results back and tell the JCVI, we didn't have time to wait, right? So then we thought, well, let's see what happens if we give the vaccines a little bit later. So all of the people who initially got the control vaccine, the meningococcal vaccine, as soon as we found that actually giving these boosters was really effective, like much more effective than we'd anticipated, we thought, well, obviously we're not just going to leave these guys blind, let them go on without a booster. Everyone's getting boosters, so we need to give these guys boosters. So we unblinded them. So we told them, you were in the control arm. If you'd like, you can come in and we'll give you a vaccine. It'll be really helpful because then we'll do your blood tests again and we'll see what happened. And actually, the lower your antibody levels have gone, the better a boost you get after you have a booster vaccine. So the longer you leave it, the more effective the booster vaccine is. Obviously, you have to trade that off with you go a longer period without any protection. So it's not quite as simple as it sounds. And then we took loads of young people and we gave them half doses, and that was, or even third doses, and that was based on that data I just showed you. And knowing that the younger you are, the worse your reactogenicity. So if you are more mature, you tend to not react quite so strongly and feel quite so poorly. If you're in your 20s and 30s, actually you feel quite rubbish. And also there were some safety signals with high-dose mRNA vaccines in those age groups of an increased risk of inflammation of the heart, of myocarditis. So a real good incentive to give them low doses. We also did a 4th dose study of all the people who got the Pfizer vaccine, and then we were giving all these new vaccines, the ones that were against just Omicron, and then the bivalent vaccine, and so on and so forth. And like I said, I could talk about it all evening, but I won't bore you. And I just wanted to show you these graphs because they are so astonishing. So I don't know how closely any of you guys followed it or if you recognize these graphs, but these are the graphs that changed the world overnight. So these are what we call the survival graphs of the phase 3 trials of the Pfizer vaccine on the left and the Moderna vaccine on the right. And what you have here is the cumulative incidence of symptomatic infection in the placebo arm that goes up into the sky and the vaccine arm that stays almost completely flat. And it's remarkable to see a graph like this in medicine, okay? There is just no other field of medicine where you can do a clinical trial and you don't need a statistician to tell you whether your drug works, right? This is incredible. I mean, this is beyond anything we had ever anticipated. We were hoping for in the region of 50% reduction in risk of symptomatic infection, and we got upwards of 90%. Okay, and this was likely largely sterilizing immunity at this stage as well, because when these trials were done, of course, the original vaccines contained the original spike protein of the SARS-CoV-2 virus, and the virus that was circulating was the original SARS-CoV-2 virus, and they were so effective. Beautiful. And then, of course, the problem was we got new variants, and then we had the impact of time. And what we can see in these charts is the waning of effectiveness over time of protection against symptomatic infection. So what we have here, you can see the black dots, the black boxes at the top are protection against the Delta variant, and the circles in the grey are protection against the Omicron variant. And you can see that for the second doses at the top, this was for people who had 2 doses of the Oxford AstraZeneca vaccine and then got a Pfizer or Moderna booster. You can see against the Omicron variant, for only 2 doses, so without a booster, you were down at 0 protection by about 25 weeks. So 6 months, you had no protection against symptomatic infection. But the boosters were remarkable. They brought that up to 40 to 60%, even after 6 months, which was great, very effective. And unfortunately, this correlated very strongly with levels of neutralizing antibodies. Okay, so this is what we call a surrogate of protection. So if you measure the level of antibodies in people's bloods and you watch them drop very precipitously over time against COVID-19, and that correlates with the protection against symptomatic infection. Now, what's very important to point out, and I should have put the other graph in because actually it's happier, but the protection against severe disease, hospitalization and death does not look like this. It's much flatter. It does decline over time somewhat, but some of that is actually just reflecting this, which is that your risk of actually getting infected falls. Your risk of getting severely ill if you get infected actually doesn't change that much, and your protection goes up every time you get a booster. So they're really great vaccines. And they saved a lot of lives. This is a graph where in the red line, so the graph on the left, we have the red line. This is the expected deaths we should have got from COVID-19 based on the number of infections that we observed and that we would have observed without the vaccines. This is how many deaths we would have had. And the grey line underneath is how many deaths we actually had. And then you can see in the graph of the right, this is the estimated number of lives that were saved by each vaccine. This was only within the first year of the vaccines being deployed. 20 million lives in the first year alone of these vaccines being deployed. And that's about 6 million each for the Oxford vaccine and the Pfizer vaccine. That is extraordinary. Okay, in the history of mankind, there is probably not a single other medicine that saved so many lives in such a short period of time. And that's not just because of the effectiveness of the vaccines, but it was also because of the mobilization, getting them into people's arms. Okay, so what it takes to do that is extraordinary. Okay, it takes all the regulatory stuff to go through, manufacturing, distribution, the people actually giving the injections, and finally the people coming forward and receiving those vaccines. 20 million lives in the first year. Amazing. So where next? So the thing that people are most excited about at the moment for the future of COVID vaccines is what we call mucosal vaccines. So obviously what we've observed is that your protection against getting infected drops quite quickly every time you're infected. So even though you're being protected from going to hospital, after 12 to 18 weeks, your risk of getting infected is not very different to what it was before you had your booster, okay? And that's a shame, because what we like is when we get vaccines that stop you getting infected, because if you can stop people getting infected, you can provide a bit of herd immunity, okay? And you can protect lots of other people from it. And what we would like to develop are vaccines that can stop you getting infected. And the place you get infected is in your nose and throat, okay? And at that surface, the immunity is very different to the immunity you have in your blood. And when I inject your muscle with an antigen or the vaccine, I'm mainly giving you immunity within your blood, okay, your systemic circulation. And actually trying to make immunity at a mucosal surface is not so easy. And what people are hoping is that we can do it by delivering vaccines to a mucosal surface. So in a similar way that we give the flu spray up the nose, people are trying spray vaccines for COVID-19. I'm going to be honest, I think most of us who have been working in vaccines for a while were not as optimistic about this as other people have been, because we have existing mucosal vaccines like the flu vaccine. We know it's not brilliant at causing sterilizing immunity at the site, but this is something that people are working on, and certainly the hope would be that if we can advance this science somewhat, we might be able to cause better sterilizing immunity at the site of infection and prevent infection altogether. And of course, the future is pan-sarbecovirus vaccines or pan-coronavirus vaccines would be even better. And this is important not just for COVID-19, but really for future-proofing. So obviously, we don't need much more evidence that coronaviruses have pandemic potential. They've done a few now, and they're likely to do more in the future. And what would be great is, instead of having to react very quickly, that we could be a bit more proactive, and we'd have vaccines in the bank that could be deployed at scale immediately, even if they're not 100% effective. If they can provide small amounts of immunity against any possible future coronaviruses, that could still potentially save millions of lives whilst we were waiting for more effective vaccines. So this is sort of a priority for the World Health Organization and people like me who work in vaccines at the moment. And that's the end of my presentation. Thank you very much for listening.